Hi everyone. Let's continue to talk about chapter 4. Please turn to page 388. And in previous week, we have talked about a few problems, including problem 5, problem 9, problem 11. So we start from problem 13. So for this problem, first we draw log 2x. So how can we draw log 2x? The simplest method is you put some value. So we want to draw this first. We want to draw this y equals log 2x. So this is x, this is y, and so we could choose a few x. So if we put 1/4, and this is -2. If we put 1/2, and y is -1. And if we put x equals 1, y equals 0. And if we put x equals 2, y equals 1. If we put x equals 4, y equals 2, and forth and so on. And if we put 8, it becomes 3. So for this log 2x, if we draw this on the xy plane, and then we put all the figures, and please, and please notice that so this is y. Please notice that x needs to be always larger than 0. So x larger than 0. So we know x equals 0 is an asymptote. Okay. Okay. And so we put this, so when x equals 1, y equals 0, and x equals to 2, y equals 1, here, it's roughly here, here, and x equals 4, y equals to 2, probably here, and x equals 8, y equals 3, probably here. So if you put all the points together, you will have something like this. This is y equals log 2x. And actually, I use different color. Actually, it is so if we could have this x equals 2 to the power of y. Okay, and so for y equals 0, x equals 1. No, this is y equals 0. We have this. We have y equals 2x. Okay, so if we want to draw y equals 2x, my bad. So, wait a minute. Okay, good. How about let's y equals 2x. So again, I use black. This is x. This is y. X equals 0, y equals 1. X equals to 2. Y equals 4. X equals 3. Y equals 8. X equals wait, this is 1. I mean 0, 1. Y equals 2, 2. Y equals 4, 3. Y equals 8. And then if this is 1/2, and then y equals what? 1/4. 1. Okay, let me check. 2 to yeah, if x is 1/2, y is just square root of 2. Okay, and then so no, this is not what I said. If x is -1, if x is -1, and this is 1/2, and if it's -2, x is 1/4. Okay, so in this case, y is always larger than 0. Okay, so which means y always larger than 0. So in this case, and then it passes x equals 0, y equals 1. So this is x equals 0, y equals 1. So it will be like this. So this is y equals 2x. So they are symmetric about this is y equals x. So they are symmetric about y equals x, which means this is the exponential function by using 2 as a basis, and this is the log function by using 2 as a basis. They are symmetric because they are each other's inverse function. Okay, so they are symmetric about y equals x. And so this dot is 0, this point is 0, 1, and the point here is 1, 0. This is 1, 0. Okay, so we use this problem to review this exponential function and log function, and it could be easily drawn by assigning the points. Okay, so remember they are symmetric, and one is x. For log function, is x larger than 0, and for this exponential function is y larger than 0, and there is asymptote. Okay, and so in this case, we have this log 2x, and it's minus. So since it is minus, we need to make it upside down. Okay, so let's draw this. Sorry. So make it upside down, but so if we make this so they are rotating, flipped in terms of x-axis. So that's why. So this is 1, 0, and then so this is minus. So this is minus log 2x. Okay, it flips in terms of x-axis, and then add 2. Okay, so it shift up to the top by 2. So it's so this is 1, 2, and then this should be the solid red line. This is 1, 0. The solid red line should be this 2 minus log x with the base of 2. So this is f of x, and we can calculate this point. This point is when y equals 0. When y equals 0, so which means fx equals 0 equals 2 minus log 2x. So which is log 2x equals to 2, and then x equals 4, right? So the x-intercept is 4, 0. Okay, so let me make it more clear. So the red line is f of x. So let me double check with the answer. Yes, correct. So that's how we draw it. First, you need to know the shape of the relationship. You need to know this. You need to know this, the shape of an exponential function and its log function, and their x-intercept and the y-intercept. And then so you could either flip. So in this case, it's a flip and then shift to top by 2. Okay. So if you still have problems, please go back to the textbook. Okay, and then state the domain, range, and asymptote. So in this case, the domain is x larger than 0, right? Because apparently x equals 0 is an asymptote. So domain, I write it here, domain is x larger than 0. And its range is y. Y is the range of y would be all the real number. And asymptote is this y-axis, which is x equals 0. And more correctly, I could say this is y belongs to a real number. Okay, and more correctly, how about I say this is from 0 to infinity. This is x from 0 to infinity, which is equivalent to x is larger than 0. So if you have questions, please go back to the textbook. So we're going to look at the next problem. So next problem is we want to find out the domain of the function. So first, if this x squared is in the power, actually x could be either a positive or negative value, but x squared is always positive. So x here could be positive or negative. So we have this, the domain for x for this is real number. Any real number could satisfy this 10 to the power of x squared. And if we look at the second term, and because what inside the log, it must be always larger than 0. So we have this 1 minus 2x larger than 0, which means 1 larger than 2x, x smaller than 1 over 2. Okay, so for the first term, we have x belongs to any real number. For the second term, it requires x smaller than 1 over 2. So we take the union of it. So the domain will be x smaller than 1 over 2 minus infinity. Okay, so it must be the domain of x must be within negative infinity to 1 over 2, because and it cannot be equal to 1 over 2, because what inside the log function must be always larger than 0. Okay, so this is the characteristic of a log function. And then let's look at problem 19. Find the domain of the function. So we need, since what inside the log, this is natural log, ln. So what inside the log must be always larger than 0. So we have x squared minus 4 larger than 0. And then it is x squared larger than 4. So it can be written as, actually we did this before. So it can be written as x squared minus 4 is larger than 0, and which is x plus 2, x minus 2 larger than 0. And to determine the domain of this x, we can write on the real axis, we could write this point which makes it equals 0. It is 2 minus 2. And then we plug in the number. For example, if we plug in 3, 3 plus 2 is 5 times 1 larger than 0. So this is plus. And if we put 0, 0, and then this is 2 times minus 2 smaller than 0. So this, we know this segment is minus. And then we can choose anything smaller than minus 2. For example, minus 3. So this is minus 3 plus 2 is minus 1. Minus 3 minus 2 is minus 5. So minus times minus is larger than 0. So to satisfy this inequality, we have this. On the real axis, we have this. And remember, 2 is not included because this is not equal to 0. So 2 and minus 2 are not included. So so the domain of this function must satisfy this inequality, and so the answer should be when you use parentheses. This is minus 2. This is minus infinity, and union with this is 2. This is positive infinity. And as you know, the parenthesis means the value of 2 is not included. So let me specify here. So parenthesis means 2 is not included. Okay. So this is also a simple one. It just tests you the property, or you can say characteristic of a natural log function. And the property is simple, is what inside the natural log or log function, it must be always larger than 0. Okay, so we just use this property. Okay, and let's look at problem 21. Exponential form. So we need to show this write the equation in exponential form. So here, you always remember the result of a log function is the exponent of the basis function. Let me write it down. Kind of catch the result of a log function. And we can say, or output is the exponent of the base to receive the value of what inside the log. Okay, the result of a log function is the exponent of the base to receive the value inside the log. So in this case, if we want to write this equation in exponential form, and it could be written as this is 2 to the power, because the output of log function is the exponent of the base is 2, and to receive the value inside the log. So it is 2 to the power of 10 equals 1024. Okay, so this is the simple demonstration of a log function. Okay, and so write the equation in logarithmic form. So the base is 10, so we have log base 10, and then because the output should be the exponent, okay, to raise this so this is to raise this to raise the exponent to this value. Okay, so if you write 10 to the power of x equals 74, it is equivalent to log 74 equals x. And if the base is 10, sometimes we ignore, so we have log 74 equals x. Okay, so if it is ignored, then you know you should put 10 as the base value. Okay, any questions? Okay, if no questions, let's keep look at the next problem. Problem 31, 10 to the power of log 45. So so if this is the output, so if y equals so we look at 31 first. Look at 31 first, and if y equals log 45, what does that mean? That means if we use the base, which is 10 because it doesn't say, so it is 10, then the output of log function is the exponent 10 to the power of y equals 45. Okay, so see, this is y. So the answer of the problem 31 is 45. Okay, so this is the definition of a log function. Okay, so you can easily convert the log function into its corresponding exponential form. And always remember the output y is the power of the same base, and to raise this raise the value to what inside the log function. Okay, and then for 33, it's natural log. What inside the natural log is exponential to the power of 6. So it could be written as, you could put 6 power, you could put power in front of the natural log, and this is 6 times natural log e, and this is 1. So it's equivalent to 6 times 1 equals 6. Okay, so any problems? This is problem 33. Okay, let's look at the next problem, which is problem 39. Evaluating logarithmic expression and evaluate the expression without using a calculator. Okay, no calculators. So the plus, the summation, or addition of log function, it is, let me see, this is equals log. It becomes multiplication inside log function. Okay, and which is log, this is 100, and so which is log 10 to the power of 10, because I read it slowly, 10 log 10. But if I didn't say the base function of the natural log of this log, it should be base 10, right? It should base 10, should base 10. And then log 10, it is 1. So which means for no, this is not right. My bad. This is 2 because it's okay. So this is 2. This is 2. Okay, my bad. My bad. This is you should convert 100 to the 10 to the power of 2 and put 2 outside the log function. And what's left is log 10, 10. And log 10, 10 is 1. So you have the answer for 39 is 2. Okay, and then let's look at the next problem. It's problem 45. It's log AB squared C cube. So it could be written as, I write it here. It's a basic property of log function. So it is equals log A plus 2 log B plus 3 log C. I believe most of you should be very familiar with it. And so for 47, it can be written as natural log, and this is x squared minus 1, x squared plus 1 to the power of 1/2. And then we could put 1/2 in front of outside the natural log, and then division within the natural log becomes subtraction. So we have this is x squared minus 1 subtract natural log x squared plus 1. Okay, so within the log function, division becomes subtraction, and then we could further decompose. This is because this is x squared minus 1 equals x plus 1 times x minus 1. This is x plus 1 times x minus 1, which is, let me write it more, x plus 1 times x minus 1, which is, so you could, and the multiplication within the log function is the summation. Okay, so its multiplication within the log function becomes a summation. So we have a natural log x plus 1 plus natural log x minus 1 minus natural log x squared plus 1. So which is the answer? So you need to be familiar with the property of this log function, and natural log function, just a specific case of it. Okay, and let's look at this, combining this log expression into a single log. So, so first of all, we look at the base. They are all base of 2. And then, so the first one could be, we put what's outside the log function into it becomes the exponent of what inside the log. So the first term becomes, we keep the same base. And then this is x minus y to the power of 3/2 and minus log to these 2 as the base, x squared plus y squared, and then 2, if we put 2 inside the log function, it becomes the power, and the subtraction of 2 logs becomes the division within the log function. So we use log 2, and then This is what within the log function. This is x minus y, 3 over 2, and subtraction becomes a division. So this is x squared plus y squared squared. So this is the answer. Okay. So let's look at the next problem, which is problem 65. Exponential log. Find the exact solution if possible. Otherwise, use a calculator to approximate to 2 decimals. Okay, so we apply the same thing. We apply the property of log function. So in this case, this is a this is the summation of the 2 log. So if it's a summation of the 2 log, it becomes a multiplication within the log function. So it is a log x times x plus 1 equals log 12. And so we have this what inside the log function should be equal. So we have this x squared plus x equals 12, which is x squared plus x minus 12 equals 0. So we have x plus 4, x minus 3 equals 0, and x equals this is plus 4 minus 3, x equals minus 3, x equals 3 minus 4. Let me double check. This is 65. This is review 65, x equals 3. Okay, so x equals 3 minus 4. However, we need to, what inside the log must be always larger than 0. So however, because x need to be larger than 0. Okay, so, and then so we erase minus 4 because we have x larger than 0, and this is x plus 1 larger than 0, which is x larger minus 1. So, but we need x larger than 0. Okay, so, and because if x larger than 0 and x, it automatically satisfies x larger than minus 1. Okay, so we put this as our constraint. And so in this solution, although it has 2 solutions for x, for this equation, it has 3 and minus 4, but we need to put the constraint. Constraint is what inside the log function must be always larger than 0. So we erase the minus. This is invalid. So the answer is just x equals 3. So any questions? Okay, so when we look at this 67, so we need to have, so we specify the constraint first. So the constraint is y minus x must be larger than 0. And let me say it's constraint. Constraint y minus x must be larger than 0. So x is smaller than 1. Okay, and once we have it, so we can convert the both sides of the equation equals as log function. So we convert, since what's on the left is the log function, we convert what's on the right to the log function. So it could be written as log 2 to the power of 4, because log 2 equals 1. Okay, so it's if we write it more step by step, will be 4 times log 2, and what outside the log function could be put into the log function, but as an exponent. Okay, so which means it is log base 2 is 2 to the power of 4, which is 16. Okay, so you have this. The both sides of the equation, they are a log function with the base 2. So you have this 1 minus x equals 16, and x equals minus 15. And let's double check if it satisfies the constraint. The constraint is x is smaller than 1. So which it is valid. It is valid. So this is the answer. X equals minus 15. Okay, so for this log function, we need to always pay attention to the constraint. Okay, to the constraint. This is constraint. Okay. So this is answer. Okay, any questions? Okay, the next question I want to talk about problem 85. So next slides. Change of base. Change of base, there's an algorithm for change of base, and you need to memorize it. So change your base. If this is log, this is b, this is x, we can change it to base a. So log a x divided by log a b. We can convert a base b to base a. Okay, so you need to memorize this. This is not hard to derive, and it is on the textbook. So if you are interested, you please go to the textbook. So for the first one, x is log with the base 4, log 15 with base 4, and then we apply the conversion to bases. It becomes log 15 divided by log 4. And if I didn't write the base value, it means it's log 10, because on the calculator, you only have the button for log 10. So that's why you need to, when you are using calculator to calculate this value, you need to convert, you need to change the base. You need to change the base. So since you don't have the calculator, I just write down the value is 1.9534. But when you are asked to calculate this, you need to change the base. Okay. Because on the calculator, you only have two log. It only has two log functions. One is log to the base of 10. Another is natural log. Okay. So for this 87, you change your basis, because on the calculator, there's no baseline for log function. So you need to convert it to base 10. So you have log 0.28 divided by log 9. Okay, and then since you don't have the calculator, okay, you round it to 6 decimal places. Okay, so for the second one, let's talk about the second one first. So it's 0.5793516. So 1, 2, 3, 4, 5, 6. You round it to the 6 decimal places, which is 1. So you take this 6. If it is 6 is larger than 5, it becomes, so it becomes 2, and then you erase 6. Okay, and then for the first one, let me click the calculators. You have log 15 divided by log 4, which is 1.9534452. So this is 1, 1, 2, 3, 4, 5, 6. And this is 2, this is smaller than 5, so just erase it. So this is our answer for 85. Let me double check. Is 1.953445. Okay, so and then answer for 87 is minus 0.579352. Okay, so yes, in the exam, you may be asked to round it to certain number of decimal places. This is how you do it. Okay. Let's look at problem number 91. Let me see. If this because this problem statement has been blocked somehow, so please allow me to turn to the page. This is a review of chapter 4 and problem 91. Wait a second. Problem 91. Okay. Compound interest. If 12,000 is invested at an interest rate of 10% per year, 10% per year, find the amount of the investment at the end of 3 years for each compounding methods. Okay, so the first is semi-annually. So for A, so for semi-annually, if it is 3 years, which means for each year or totally, it will compound 6 times. Okay, so to calculate this amount of investment at the end of 3 years, you have this 12,000 times 1 plus, and because it says annual rate is 10% per year, but it compounds semi-annually, so you have 10% divided by 2. So each time you compound 10% divided by 2. Okay, because 1 year is 10%, half year is 10% divided by 2. And then it compounds 6 times. So to the power of 6. Okay, because 3 times 2 equals 6. And the answer is, you need calculators for this. Okay. This is the result for answer for problem A. Okay, and so for monthly, so for B, if it has 3 years and it compounds monthly, so it compounds 3 times 12 equals 36 times. Okay, and then so the equation becomes the initial capital 12,000 times 1 plus, because it compounds monthly, and for this rate of interest rate is 10% per year, and if it's monthly divided by 12, and then it compounds 36 times. So it becomes 16, 178, 18. Okay. And for problem C, it compounds daily. So 3 years, each year has 665 days. And So which is 3 times 665 1095. Okay, and so you have this 12,000 multiplied by 1 plus annually is the interest rate is 10% per year and divided by day, so which is 365, and compound this 1095 times, and then so we have this 16, this is 197.64, like this. Okay, and the last one it compounds continuously, and if it is compound continuously, it can be written as 12,000 multiplied by e to the power of 10% times 3. Because this is Rn, so because the exponential function, this is just the annual rate. This is R, so this is annual rate, annual interest. This is the annual interest rate. Because we have exponential function, it will be equal to 1 over n to the power n, and it's very large. Okay, so if it compounds continuously, which means n is very large, it becomes this e to the power of r times 3 years, and its result is 16,198.31. So if it compound continuously, you need to memorize this. So it becomes 4t. This is more specific. So we have this P is capital. So the total amount money equals P E to the RT. R is annual interest rate. And T is number of years. R number of years. Okay, so you have to memorize this. And let me put this P on the bottom. So you have the formula on the very top. Then you won't be confused. So I may erase this. This is P is the initial capital. Okay, this is P e to the power of RT. And one thing to notice that is, if you notice these two, the difference is just $1. So which means 1095 is large enough because it converge. So if it compounds daily, you could use this simple, because this exponential function is simpler, you could use this exponential function to represent the compound daily result. Okay, so this is 4 types of compounding methods. And if you want to know the proof of this continuous compound formula, please look at the textbook. Okay, it has the full proof of it, but we don't explain this in the review. Okay, so let's look at the next problem is problem 93. It is also compound interest. So a money market account pays 5.2% annual interest compounded daily if 100,000 is invested in this account. How long will it take for the account to accumulate 10,000 in interest? Okay, so we apply this compound daily formula. So the initial capital, so the total amount money, equals 100. This is initial capital, 100,000 multiplied by 1 plus its annual interest is 5.2%, and then this divided by 365 because it compounds daily. And then so have 365 n. Suppose it need n years. So each year has 365 dates, and it equals its initial capital plus interest. Interest is 10,000, which means it is 110,000. Okay, to solve this, we just take log. So first, I would put this. This is 1 plus 5.2%, 365. This is 365n, and what's on the right is 110, 30. This is 100,000. So so it can be erased. And then we could put we take log function to the both side, to the left side and to the right side. So if we could put log, and then once we put log function to this, and for the exponent, we can take the exponent outside the log. So it's 365 log 1 plus 5.2% divided by 365 equals log 11 divided by 10. This is 365 n. So n is n equals log 11 divided by 10 is 1.1, and then this is log and then it's 365 times log 1 plus 5.2% divided by 365. In these calculators, and then the results 1.833 years. Okay, so although it uses calculators to solve it, this is how we solve this. This is power. This is the unknown is in the power. So we apply log function to both sides of the equation and then solve n. Okay, this is how you solve it. Even though in this case you need to use a calculator, And maybe in the exam, you may be given another problem which doesn't need a calculator. Okay, but this is important. Please know how to solve this kind of problem. Okay, so let's look at problem 97. So problem 97, cat population. The stray cat population in a small town grows exponentially. In 1999, the town had 30 stray cats, and the relative growth rate was 15% per year. A. Find a function that models the stray cat population NT after T years. So it gives us some hint. So it says this cat population grows exponentially, and its relative growth rate was 50% per year. So for A, so by given these two, you need to immediately write this is NT equals, and the initial cat population is 30, and since it grows exponentially, it has exponential function, and then this is R T. R is annual growth rate is 15%. Okay, so this is our first equation. So let me put value of R into our equation, which is exponential to the power of 0.15 t. Sorry. So any questions? Okay. So once you lay out the equation, the remaining problem shouldn't be just easy to solve. So find a projected population after 4 years. And so we have N4 equals 30 e to the power of 0.15 t. And then times 4, because times 4, and yes, in this case, you need a calculator, which is 30 times e to the power of 0.6, which is 54.66, approximately 55, because for number of cats, it must be an integer. So if you find 54.66, then we just make it 55. Okay, so for problem C, find the number of years required for the stray cat population to reach 500. So we have this equation, 30 times e to the power of 0.15 t equals 500. So if there's an exponential function in the equation, it means we need to apply a natural log to both sides. But before we apply natural log, let's make some rearrangement, which is this is 500 divided by 30. And then we can apply natural log to both sides. This is natural log, and this is I make it 50 divided by 30, because 10 just erase. And then we could put we could put the exponents within the natural log outside the natural log, right? So it's 0.515 t times natural log e equals natural log. This is 50 divided by 3. And this whole term is 1, right? Because natural log e is 1. So t equals what? T equals 1 divided by 0.15 multiplied by natural log. And this is 50 divided by 3. and which is, and let me double check, which is 1 divided by 0.15 multiply natural log. This is 50 divided by 3, which is 18.75, which is approximates 19 years. Okay, so which is the answer? Okay, so the tip is if you see the power, if you see the exponent, this is the exponent in the equation, and then you need to apply log function, and if it's exponential, if the base is an exponential function, and then you need to apply natural log function to both sides of the equation. Okay, but if it's not, just log the log with the base of 10 would solve this problem. Okay, so any questions? If you have questions, please go back to the textbook. And then let's look at the next problem, which is problem 101. Okay, problem 101, radioactive decay. The half-life of radium 226 is 1,590 years. A, if a sample has a mass of 150 milligram, find a function that models the mass that remains after T years. So we look at this equation. So the so-called half-life, half-life of the radioactive decay is it can be written as this: the total mass N of T is the initial mass times 1/2 to the power of T divided by 1,590. Because its half-life is 1,590 years, it means every 1,590 years, its mass decreased by half. Okay, so this is the equation that you can list. So problem B is what? Find the mass that will remain after 1,000 years. So we have N, T is 1,000 equals the initial mass is 150 milligram and times 1/2. This is 1,000, 1,590. Yes, in this case, you need a calculator, which is 96.998 mg. So let me double check the answer, which is here. Is here. You see, this is chapter 4, problem 101. Yeah, it's almost 97 mg. Yes, this answer is correct. And then after how many years will only 50 milligram remain? So for problem C, yes, this is what remains is 50 gram, and initial mass is 150 milligram, and this is 1/2. This is T 1,590. So so this is an exponent. You have exponent, and then you have a base function. So to solve this equation, you need to apply log function to both sides. So, but before that, let's make it 50 divided by 150 equals 1/2. This is T divided by 1,590. 0.1590. So this is 1/3. Okay, and when we take log function we apply log function to both sides. So we have log 1/3 equals log, and then exponent could be put outside the log. So this t/1590 log 1/2. Okay, so you have this, you have t equals t/1590 equals log 1/3 divided by log 1/2. Okay, so you have t equals unit calculators. So t equals 18.75, which is approximate 19 years. Okay, yeah, this is how we solve it. Okay, so if you have problems, go to see a textbook. Okay, and hopefully you don't have any problems regarding this. Well, this kind of problem is also regarded as a basic problem. Okay, let's look at problem 105. Problem 105, pH. The hydrogen iron concentration of fresh egg whites was measured as the concentration of H plus is 1.3 multiplied by 10 to the power of minus 8 m. Find the pH and classify the substance as acid or basic. So we know that high concentration of H plus of this hydrogen iron, it will be acid. So the pH value is defined by minus log and the concentration of this hydrogen ion. Okay, and so if we put the concentration into this H plus, so we have minus log 1.3 times 10 to the power of minus 8, and it is because the multiplication within the log function is equivalent as the summation of two independent log function. Okay, so the multiplication within the log function could be equivalent to the summation of two log functions. So which is minus log 1.3 minus 8, which is 7.88, and which is it value larger than 7, which means this is not acid, this is basic. And if it's smaller than 7, it means it is acidic. Okay, so it put a minus sign here. So the definition of pH value, it put a minus sign on the front of log, and the reason to do that is it want to erase the negative value, and then so the larger this pH value, it means the fewer concentration of this hydrogen iron. Okay, so the larger of the pH value, the fewer concentration of hydrogen ion, which means it's more basic. pH value, fewer concentration of H plus, which means it is more basic. Okay, so we use 7 as a threshold, and if it's larger than 7, it means the concentration of this H plus is very small, which means it is more basic. Okay, so high concentration of H plus, it means the liquid is acid. Okay, let's look at the last problem. It's problem 107, Richter scale. If one earthquake has magnitude 6.5 on the Richter scale, what is the magnitude of another quake that is 35 times as intense? So we need to know the definition of Richter scale. And we have log. The definition of Richter scale is defined by log. So we have R divided by R0 equals 65. And R should be the vibration magnitude or energy of the earthquake. Let me double check. Okay, or that can say that's the magnitude, intensity of the earthquake. Okay, R is the intensity. This is the intensity. Intensity. And R0 is the reference intensity of the earthquake. Okay, we need to have a reference, and it could be, you can assign any intensity of any earthquake as a reference. So, but in here we have a specific reference for the Richter scale. So the definition of Richter scale is it is defined by log. The intensity, because the textbook use I, so we follow what is defined in the textbook. Is I divided by I0, and it's 60.5. And it says there's a new earthquake, and its intensity is 35 times the original one, and they have the same reference intensity. And how can we solve this? And if you remember, the multiplication within the log function becomes the summation of two independent log function. So you have this I divided by I0. So you have this log 35 plus 6.5, because we know this is 6.5, and then which is 1.544, and yes, you need a calculator, plus 6.5, which is 8.04. So this is the magnitude. This is the Richter scale of the new earthquake. Okay. All right. And then we finished the review of chapter 4, and I will publish the answer. I will ask TA to publish the answer to the Google Classroom. And this is all for the review of chapter 4.